power distribution network a way forward for energy savings. So I request our chairman, Professor Ramana Bhanwathu, to start the proceedings.
Thank you, Honorable Secretary. Thank you. And thank you, Conversar. Instead of Indian State Central Energy Conservation Mission, the Telangana
రీసౌండ్ వస్తుంది సార్. సార్ రీసౌండ్ వస్తుంది. రీసౌండ్ వస్తుంది.
Resound.
I request all the participants, please mute your.
Yeah, that's correct. So thank you. Today's convener, Professor Satish Kumar sir, FIE, and our Honorable Secretary Garu, and today's our chief guest, Srimati Anila Vavila, Vice Chairman MD, and our main speaker, keynote speaker, Dr. K.S. Gandhi Garu, FI, former DG NTPC, and all eminent engineers who attended today, N.S. Rao Garu, Dr. A.S. Rao Garu, Ramkishan Rao Garu came from USA, Gopal Krishna Garu, and అందరికీ మరొకసారి ఇంధన పొదుపు వారోత్సవ శుభాకాంక్షలు తెలియపరుస్తూ all past presidents and past vice president council members of IEI and past chairman, past Honorable Secretary committee members and all corporate members, IETC members of Energy Commission, Mission, budding engineers and ladies and gentlemen, good evening all. Today I feel it's a great privilege and honor to be admit this August gathering and extend a warm and healthy welcome to our chief guest Srimati Anila Vavila Garu, Vice Chairman MD, TG Redco, and Dr. K.S. Gandhi, FI, former DGM NTPC, and all of us to this Energy Conference Day. We congratulate to Srimati Anila Vavila Garu, VC MD Redco, TG Redco, for receiving the Best Energy Efficiency Award 2025 for Telangana from Government of India in Delhi. The National Energy Conservation Day is observed annually in India, December 14th, to highlight the importance of energy conservation, promote awareness about the efficiency energy use. The day is celebrated under the guidance of Bureau of Energy Efficiency (BEE), which operates under the Ministry of Power and Government of India. The object of Energy Conservation Day to promote the energy efficiency technologies, carbon footprints, increase the use of renewable energy sources, and raising awareness among the individual, business, and industries about the energy conservation practices. You can contribute to the energy conservation by switching off lights and appliances when not in use, using the energy efficient appliance, reducing the use of non-renewable energy, and opting for solar and wind energy, carpooling of the using of the public transportation, and energy conservation for crucial for enhancing of the sustainable development, reducing the greenhouse sustainable development, gas emissions, and mitigating the effects of the climate change, preserving the resources of future generations. So today, I think you might have seen our Srinivasachari Garu, our former committee member, wrote a very good editorial in Eenadu in the morning. I think all of you seen, and our all persons from Netizenbal. Thank you, Vandana. So I'm requesting Kinder to follow. Proceeding. Let's go on. Unmute Sachin. Unmute.
Thank you, sir. Good evening, everyone. Respected Chairman, sir, Dr. Professor Ramana Nayak, sir, and also Honorary Chairman Mari Ramesh Garu, and today's chief guest, Vanilla Madam, Anila Vavila Madam, and also Dr. K.S. Gandhi Garu for coming forward to develop an expert lecture on the occasion of Energy Conservation Week celebrations. I thank you, sir. Thank you for your gesture here for delivering an expert talk on this. I am very fortunate to introduce our today's speaker, Dr. K.S. Gandhi Garu. He was born in 24/6/1946, and he completed his Bachelor of Engineering the Electrical from Andhra University College of Engineering, Walter, in 1967, and MTech Power Systems from JNTU Hyderabad in 94. And he obtained his PhD degree from JNTU Hyderabad in 2005. And the thesis, Market-Based Tariff Reforms, a Framework for Indian Power Sector. He has worked in the APSCB in the Vidyut Sauda from 1970 to 1975, and the Project Engineering Division BHEL from 1975 to 1980. And in addition to that, as the Deputy General Manager in NTPC from 1982 to 2003, Power System Engineering, Quality Assurance, Commercial Inspection and Project Management. And also in Engineering Staff College of India, he offered his services as Senior Faculty in Power and Energy from 2004 to 2005. And as an advisor and consultant in the Vijay Electricals 2004 to 2007, Simhapuri Energy Limited 2007 to 2012, Mega Engineering and Infrastructure Limited. And also he taught academically, he taught power system reliability, gas insulated substations and high voltage engineering to MTech EPS batch for 7 years. And his areas of interest are regulatory reforms, regulations, grid code and electricity markets, high voltage engineering, power system related areas. He is a project management training or seminars or workshops on climate change, net zero, as well as the renewable integration. The professional membership is a life member for IIPE and fellow of Institute of Engineers, chartered engineer. Sir, I heartily welcome you to deliver an expertise. Your expertise definitely will motivate the young engineers and also the students of research as well as the MTech scholars. Many MTech scholars and research scholars are joined this event. Welcome, sir. And from the Institute of Engineers, I heartily welcome you to deliver the lecture. Thank you each and everyone. Thank you, sir.
Sir, can I proceed now, sir?
Yeah, you can, sir.
Please proceed, sir.
I want to share my this thing. I can Is it visible, sir?
Yes, sir. Yes, sir. Go ahead, sir.
Thank you, sir.
Welcome, sir. Gangadhar.
Thank you, sir. Naskar, sir. Thank you, sir, Satish, sir. In fact, for your good words about me. Yes, I was for last many years. I was in power sector. Of course, I mean, the Institute of Engineers Telangana chapter is not new to me, and Telangana center, because here I have given a number of, at least 5 to 10, 10 lectures, 10 papers I presented earlier. In 2003 also I have given one paper on one presentation on markets and transmission pricing, congestion management, and again, different occasions. Thank you, sir. Thank you for your the opportunity given to me. Well, suddenly, of course, one thing is that yesterday evening only Professor sir asked me. Yes, I said that definitely whatever, yes, I will definitely do my best because of this energy conservation day today. Happy Conservation Day for everybody. And let me just give you some sort of very small ideas about the conservation of electricity and this loss reduction. That's what my topic actually. I want to focus on loss reduction through the smart grid demand response in distribution, and that energy efficiency demand response. See, otherwise a lot of initiatives are there already in the system for loss reduction and energy conservation. Basically, I want to just give some emphasis on the demand response. That's what I want to convey, and they just let me but another 45 minutes. I think I will close it, sir. Yeah. Sir, actually, the energy conservation, what is energy conservation? Energy conservation does not talk about reduction of energy, consumption of energy. Suppose if we say that you conserve food, conserve water, conserve energy, if you say that conserve food, it doesn't mean that we eat less. Or conserve energy doesn't mean that you reduce your consumption, although intentionally you will have to do it, that is different. But it does not mean that. It means that you do it efficiently. Whatever you use it efficiently. Suppose if you say that conserve water, it means you use the water efficiently. That means the losses you have to minimize, optimize the usage and minimize the losses. The focus here on this energy conservation is basically it is on loss minimization. That is the concept here. Loss minimization is the focus in energy conservation. So how do we get it? That is what actually different methods are there, and that we'll see just one by one. Energy Conservation Act was there in 2001 and there is an amendment in 2010. But basically in amendment, in fact, it was amendment focused on the components at the consumer end, the receiving end. The energy efficiency, that means end use efficiency. That is what is the concept here. And the electricity policy of National Electricity Policy 2021, of course, that was their amendment. Earlier it was 2005. That also refers to energy conservation, basically as a loss reduction. So that is what actually the focus. Energy conservation means energy loss reduction and increase the efficiency. There are a number of different areas are there. For example, in thermal power plant, everybody will work and every day there is continuous mounting on the heat loss. Heat rate. Heat rate improvement is a big conservation itself. Heat rate improvement. For that there are so many areas there. How do you control the heat rate improvement and all that? Okay, fine. Now with this actually, what is that I am trying to just bring out? You see, in the electrical distribution systems, see, actually, I don't have the slides actually. I got my own paper. I want to just read out this here. Distribution losses, particularly in the distribution sector, electricity distribution sector, the losses are basically technical losses and commercial losses. Of course, everybody we know it. These losses are collectively termed as AT&C losses, aggregate technical and commercial losses. The factors contributing to the technical losses are briefly the lengthy distribution lines, inadequate sizing of the conductors, low power factor, DTRs not located in the load centers, voltage regulation not properly controlled. Following then what are those confusions? Commercial losses. Commercial losses are discrepancy in meter readings, tampering the meters, and revenue collection efficiency. Only very simple concepts here. AT&C losses are defined as 1 minus billing efficiency into collection efficiency into 100, where billing efficiency is total units sold in million units by the total input in million units. And the collection efficiency is the revenue collected by the amount billed, that is billing efficiency and collection efficiency. That's how these AT&C losses are defined. Now, how do you mitigate the AT&C losses? HVDS, high voltage distribution systems. Yes, this is a very established practice, and then it is all going on. Very much this DISCOMs, they are doing very much in HVDS. I also worked in HVDS project, high voltage distribution schemes when I was with Vijay Electricals. They were doing this 11 kV distribution systems, and that is that in the Vidyuteekan projects, REGY schemes. Then amorphous core transformers, of course, for loss reductions in the transformers and low load losses reductions, and reconducting, upgrading the DTRs. So these are the mitigation, things. And now I will come to that actually what is actually how do you further control? Keeping the distributed generation close to the load centers, commissioning new substations, conducting regular energy audits to assess areas of high losses, assertion losses. Okay. Reactive power compensation, this is another important area to control the losses, where you have your own compensation at the receiving end. And however, these measures, whatever I just mentioned, these measures are typically require the large capital expenditure, large capital investments that are usually undertaken to meet T&D capacity augmentation requirements rather than the proposed reduction of the losses. The concept is the focus was not the losses minimization, but this is all augmentation, the capacity augmentation, and the T&D upgradation and all that. Loss reduction impact of such T&D infrastructure projects are usually regarded as ancillary benefits, not central to their respective business areas. Business areas are basically on the augmentation and those are capital investments. But loss reduction with the existing infrastructure, we can focus loss reduction through the smart grid. I will not go into much in detail of the smart grid architecture and smart grid technologies. I will not go, but only the areas how it helps in the loss reduction as well as carbon footprint emissions reduction. How it helps, basically, that only I will focus here. I will not go into the smart grid architecture and then the components in that and this intelligent devices. All those things I am not going in detail. Only, basically, I will focus on the demand response. Okay. What is the demand response? I will explain here now in the next. As it goes, demand response is because see we have two flaws on the distribution side in our country, and basically this is all maybe anywhere many places, many countries. The distribution flaws are, one is as a customer, as a consumer, he doesn't have any knowledge on the price, whatever he is paying, and the real-time price or whatever, the price and the anticipated or expected prices during peak hours of the day, or peak hours, or the next season, or like that. He doesn't have any knowledge. He doesn't have any control. First of all, knowledge he doesn't have. At the same time, he doesn't have any control also. That is one flaw in the system we have. That is the price. We don't have any price control, that the customer doesn't have any price control. He cannot control the price and he doesn't have knowledge. Whatever the DISCOM, probably the DISCOM, whatever the DISCOM is buying, at what price that DISCOM is buying from the generators or from the wholesale, he doesn't, as a customer, as a consumer, he doesn't have any knowledge. Another one is that the reliability aspect, that at the same transformer, he doesn't have any discrimination. See, the transformer and the customers, the consumer, or the feeder, in the same feeder, the different customers cannot have different reliability aspect. Although the consumer may be, he may be ready to pay or ready to spend probably more, whatever is required for his reliability. Reliability means no interruption for 24 hours. He may be ready, but you cannot have individual reliability controls as far as the same feeder or the same transformer is concerned. These are the two flaws in the distribution management as on today. Both are addressed and mitigated in the smart grid phenomena. Smart grid. Both are addressed. How the price, the customer will be able to know what the price he is paying, a real-time pricing, and also he can also be told what will be the price at which he will be charged, probably at the same evening peak, probably. So with that phenomena will help him to control the load on his own, or probably the utility can do some sort of provide some incentive. The utility can provide some incentive to the customer to think of mitigating his or probably controlling the his demand during the peak hours. The peak management. So indirectly, the smart grid, this is possible in the smart grid. Yes, this is possible in the smart grid phenomena. So that means in the smart grid, you are focusing on the peak management. Once you have the peak demand peak management, that automatically gives a lot of savings in the energy savings. That the losses will be minimized. Lot of losses will be minimized. And that losses will also, the loss reduction is equivalent to your carbon reductions, carbon emission reductions to that extent. That means the flaw which the distribution flaw, that is the number one flaw, that is as a customer doesn't have any knowledge on the pricing or does not have any control on the price. So that means this can be taken care in the smart grid. So the smart grid provides knowledge to the customer. Customer can sense the price at which he will be charged in the evening peak, or probably in the next season, or whatever way the utility provides. Utility gives the information to the customer. He can just, once the customer wants to control the demand, not only customer wants, customer can definitely control his demand during the peak hours, or probably on any time, that particular this thing. Suppose if the customer is not doing that, the utility also can have control directly on the customer side, end use. The utility also can control the end use. Any control on the peak of the demand of the day, that will have a lot of impact on the loss reduction. That will help in the loss reduction. That is number one. Number two, reliability. Reliability also is possible here, although may not have much impact on the loss reduction, but definitely in the same feeder, the different customers can go with different reliability provisions. It is possible during smart grid. So those smart grid phenomena we will not probably go into detail, but how it helps the smart grid, how it helps the demand response. Basically, the demand response and demand side management. There are two aspects we will have to understand. Demand response is one thing, and demand side management. Demand response is actually the end use, that is device, the price to the device or the appliance, the device or the appliance at the consumer side, at the consumer end. At the consumer end, he can provide, the utility can provide good information to the consumer. Consumer can understand, yes, my particular device or particular appliance, if I control or manage the operation of it by switching off, or probably by controlling it, or maintaining instead of evening peak, instead of three ACs, only two ACs probably, or one AC, maybe something like that. That type of control during peak will help in the loss reduction. Loss reduction is nothing but energy conservation. You are conserving energy through this phenomena. Okay, that is what my idea of bringing out the concept of demand response. And demand response is possible. Today it is not there, and it is possible smart grid phenomena. Smart grid is coming up in a big way, and once the smart grid or real-time pricing or the price, the incentives, the price incentives. Suppose if the utility can offer some incentive to the consumer in the form of whatever the utility decides, whatever it decides, in the form of some incentive in the financial, in a monetary incentive or some other way, it can say that you control your demand during this peak or today's peak hours, so and so hours between that period, and then you will be compensated or you will be rewarded like that. This is what the smart grid has the potential to reduce energy losses. This is what actually from generation sources to the end users, and in the T&D network using the existing power infrastructure. That is the focus here. The focus here is the existing power infrastructure. Earlier, we were targeting the loss reduction through various investments like reconductoring and changing changing the conductors and also the HVDS. Those are all very large, investment oriented, mitigation things. Now with this smart grid, with the existing infrastructure, I can mitigate the loss reductions to the extent whatever is possible. End users, here end user efficiency, end use efficiency. That means the right is right at the consumer end. Consumer, and it is consumers device control, that is appliance control. That is what possible here in this particular area. The industry experts agree. Yeah, industry experts agree. Energy efficiency is the most technically and economically viable near-term option. Near-term means this is the most in the short-term option for power industry to reduce its energy losses and thereby reduce the carbon footprint. Any energy loss is carbon loss in the reduction in the your emissions. Any loss, equivalent, straight away results into your carbon footprint reductions. That is the GHG, that is the greenhouse gases, GHG emissions reduction. Every 1 kilowatt hour unit, almost it generates carbon dioxide. Your greenhouse gases nothing but carbon dioxide only. Let us think of carbon dioxide only. And CO2 for each unit generated electricity, kWh, is almost 6.6 or 0.7 kgs of the carbon dioxide will be emitted. 0.6 or 0.65 like that, 0.65 like that, it will be emitted. Kgs of carbon dioxide. So any loss, reduction, that means to that extent your carbon footprint is also reduced. According to EPRI, it's a EPRI, they have given a lot of reports on particularly on the demand side management, and then this distribution distribution response areas. They have given the practical, and they have studied not only reports, but they made a lot of practical studies with different utilities, and then utilities in US, and then they have brought out good reports. So one of the reports I picked up, and then I have just tried to understand how it goes. According to EPRI, smart grid could potentially reduce the annual energy consumption by 56 to 200, that means low and high, billion kilowatt hours by 2030 in the US, which corresponds to 1.2 to 4.3% of reduction in the projected retail electricity sales. That means energy consumption that will be reduced there. Because of this, you are intentionally doing it. That is through demand response. Demand in energy efficiency, in the end use energy efficiency, then voltage control, these are the tools actually through smart grid it is possible, and this will result into this the reduction in the losses as well as in the it improves the the losses in the reduction in the losses as well as the reduction in the your emissions, gas emissions, that particularly carbon dioxide emissions. Combined impact of the mechanisms of smart grid has an estimated reduction of GHG. GHG means greenhouse gases emissions. Greenhouse gas emissions, basically we can look at only carbon dioxide. GHG is nothing but CO2. And emissions equal to 60 at the low end and 211 million tons of carbon dioxide per year by 2030 in US, equal to that is by this type of, by using this smart grid applications. That's what I mean to say. By using this smart grid applications, demand response and end use efficiency applications and all that, 1.2 to 4.3 reduction in the losses, and that will be equivalent to 260 to 200 million tons of carbon dioxide per year in 2030, and which is equivalent to 14 in the low end, lower side, and 50 in the higher side million cars. 50 million cars into zero emission vehicles into each year. Each year it is equal to so many cars running on the with running on the zero emission without any equivalent to zero emission cars. So these are the things actually want to this thing. What is smart grid? I will not take much time. It is not. I will not go into the architecture and all that. That will leave it for a moment. Probably that is not important for me, because you see here yeah. Now you see here some of these. Now let us see some of this comparison between smart grid and today's grid. Today's grid is well, as I told, there are two flaws in the distribution side. One flaw is the consumer does not have any knowledge on the price at which he is paying, or at which he will be charged during peak hours, or probably and all that. And at the same time, we don't know also. We don't have any different today. We don't have any different mechanisms for pricing aspects. We don't have. For example, we don't know what type of price the utility is buying, at what cost is buying from the wholesale generators. That we don't know. As a consumer, we don't know. And as a consumer, we also don't know at what peak hours, probably today evening peak, or in the next season, how much we will be charging. The utility will be charging. That also we don't know. So those that type of thing can be very much addressed here through the grid, smart grid. Okay, the smart grid to consumer participation. Here, the focus here in this consumer, in this smart grid, in the demand response concept is the consumer is very active. Consumer, he will be very active. He will be fed with a lot of information and price signals, and also sometimes even with incentives, everything possible. It is all possible here. But in today's grid, as I told, the consumers are uninformed. They do not participate. Consumers are not active in that way. And smart grid involved consumers demand response to distributed energy resources. And the demand response is a very important concept in the demand response is demand response and energy efficiency. Efficiency improvement and demand response, these two are very much very focused concepts in the smart grid. Okay. And the accommodation of all generation and storage options. Here, of course, these are some of these things I have brought out here. And these were not okay. We can see that what is the difference, major difference between the today's grid and the smart grid? And some of these, shortcomings in the present this thing, grid, they're all addressed in the optimization of the assets of operation of efficiently. Okay, I'll just skip all these things. Not okay, this is all for academic purpose, okay. But basically, when we are focusing on the losses, these are very important. That is the demand response is very important, and also end user efficiency and peak load, peak demand. I'll say control, peak demand control. So there's another concept is called demand side management. Demand side management. Demand side management is shifting the loads and peak shaving, and otherwise those techniques are already, the utilities are very much doing it. They will be doing that. Suppose if they want to do the peak shaving, probably they will suppose load shedding is one problem, one option, they will happily and very conveniently resort to. See, load shedding is not the solution for any suppose if any market behavior, suppose if you want to see the pricing, load shedding will not help. Load shedding, if you want to control the demand, load shedding is not the solution. If you want to control the demand means demand is more suddenly, and compared to your resources, generation, and the generation is not meeting your demand. So suddenly demand, it's not the only solution of control the demand by means of load shedding. Load shedding is not the only the solution. But what is then what is that solution? Demand response is solution. Okay, demand response is the solution, and also demand side management, and these are the mitigating solutions. So that means when there is demand increasing, that the demand is more, and then compared to generation in the peak hours, then why load shedding is not the solution. Demand response is the solution. So in the process, in the demand response, what you are doing is you are controlling your own demand, you are controlling your own devices. In the process, you are also maintaining the losses. You are also helping the losses in the system, so that the overall the losses will be optimized. I mean, losses will be into the supply. Your resources consumption also will be affected. Smart grid mechanisms for energy efficiency. From utilities perspective, smart grid can be viewed as a means to further 5 primary goals. These are: enhance customer service, improve operational efficiency, enhance demand response and load control, transform customer energy use behavior, support more utility energy efficiency investment. Okay, some of these things I will just have given here, but not much to discuss it because it's okay. See, some of these, suppose large buildings, this continuously commissioning means large buildings. There's some actually this I have taken from the EPRA report. EPRA, they have made the actual the impact of this smart grid applications, and then how much practically how much value, how much what is the impact of it, and in terms of the loss reductions they have considered. They have given the figures also, and that means here in the continuous commissioning of large commercial buildings by 2030. Of course, they have given the anticipated based on the studies and the experiments made at the current scenario. So they have projected to 2030 scenario. See, what is that continuous commissioning means? See, commissioning means in the the large buildings, large commercial buildings, like commercial houses, like malls and other buildings, then the devices, maintenance of the devices, that it will be continuously if they do it, probably. So that will have a lot of impact on the consumption as well as on the efficiency of the end use efficiency. So that they have projected here, lot of improvement, and they have given the figures also here. Okay, improved operational efficiency. I'm just quickly running through. The mechanism for energy savings and carbon emission reductions. Reduce line losses, reduce transportation requirements through automated meter readings. Because the meter readings, you don't have automated meter readings means, at the consumer end itself, you take the readings itself. And that is what automatic readings. And you don't have to, about the line losses. And indirect feedback to consumers and energy use through improved metering and billing, these things. A smart grid has the potential to reduce energy losses that occur in T&D system using existing power infrastructure. Okay, so then we go through that quickly. Demand response and load control. Mechanisms for energy savings and reduction in carbon. Okay, the mechanisms for energy savings and reduction in carbon emissions, carbon emissions, energy savings through peak demand reduction. This is one area where the consumer can help and the utility can save the energy by means of energy losses. And that is saving the energy means saving the nothing but energy conservation only. That is what my concept of. I mean, that is what the concept is. And if you save the energy, if you reduce the losses, if you save energy, that means you are conserving the energy. That is called energy conservation. Energy savings through peak demand reductions. How do you do that peak demand reduction? Peak demand reduction means what? The consumer will have some control. That smart grid definitely the consumer the utility has got access on the consumer's end, no problem. But the utility can shave the peak on his own. But without the utilities interference, the consumer can control their own peak demand, his own peak demand, or based on what? Based on the price signals he is fed with. The price signals he is fed with, or probably the incentives he is getting. Probably for that also the peak demand. If you control the peak demand, a lot of savings will be there. That is the concept here. If you control the peak demand during the day, the peak demand, if you control, or if you shave the a small reduction in the peak demand, it will result into lot of generation when there are lot of energy losses. There are lot of energy savings will be there. Either deployment of renewables to reduce peak demand. Okay, that of course, this is all the renewables also. Now we are talking of renewables, a lot of integration and all that, and a smart grid will help, although it may not result into reductions in all that, these carbon reductions or loss reduction, but that will facilitate renewables in the peak demand. But suppose if you have a battery energy systems and probably the energy storage systems, and immediately within no time you can bring it in the peak hours. Reduce operation of less efficient peaking plants. Then what is demand response? So the whole thing, the focus is here is energy conservation through demand response. That is the focus here for this entire presentation here. The demand response is, demand response DR refers to the mechanism to manage the demand by customer in response to the supply conditions. Supply conditions. That means during the daytime or during peak hours. So that time the consumer can have control his own demand. how do you, what is the motivation? Motivation is definitely the utility can provide the price signal to him. Yes, of course. Today, if I know my price, today evening peak, what is my price going to be? Then definitely I will take care. Definitely I will check my devices, and probably wherever possible I will do it. This thing, not that the consumer is not is not indifferent to his own energy management. Definitely he will do. But today is not happening. Today is happening, the consumer is not aware or actually is not motivated to just look at his own demand. So that is what is happening. So the utility can provide some price signals, not only price signals, some incentives also can provide to the consumer. If you provide this thing during peak hours, if you reduce by 1 kilowatt or 2 kilowatt from each household, well, it will help the utility to stabilize the system, and also a lot of savings will be there in the losses. For example, customers reduce their electricity consumption at critical times or in response to market prices. Okay, if he knows, if the customer knows that what is the market price, that is price signal. Demand response can be broadly two types: incentive-based demand response or time-based response. Of course, time-based means time of the day, TOD pricing. Anyway, these are the things actually I want to bring out. And incentive-based DR includes direct load control. Incentive-based DR includes direct control, load control, interruptible, curtailable rates, demand bidding, buyback programs, capacity market programs, and ancillary services market programs, etc. I mean, that details, of course, I'm not going to do those details. Ancillary services means, you see your reactive power. Ancillary services in the power system basically deals with the services are for this frequency control, that is active power control, and the reactive power control for voltage control, and the black start arrangements. Okay, and those are the ancillary services. Time-based rates, including time of use rates, critical peak pricing, and real-time pricing. See, these are not just simple concepts of academic concepts. These are very much possible to put in place, place, and then affect the system, so that the results are. Whatever results are aimed, whatever this thing they are obtained. Through what? Through the tools we have. The tools are very much available, and things are there, the technology is there, everything is available. But that has got to be put into implementation. That is what is actually required. So these are the other, particularly EPRA, they made a lot of reports. Actually, I have made some report, picked up some report, and they have given a very detailed report. And in that, they have given completely in if the percentage of this demand response consumers, this much is there, and how much it will result into loss reductions, and which is equivalent to what is the carbon reduction. They have even estimated. They have an estimated this is loss reduction equivalent to what is the carbon reduction, emissions reduction, carbon dioxide reduction. So that also they have given, indirectly that also they have estimated. So that type of things is possible, and energy conservation through loss reduction, and that too through distribution, the demand response and the demand control is one area where probably we can think of to big way. In future, that will be the customers are presented with options as to the variations in the quality of service that they are willing to allow in exchange of various incentives. If the customer wants, he can just definitely, he will control his demand. Or if the customer is motivated by the utility by means of some incentive, definitely that will also help. Whatever way, but the point here is the customer, the consumer, or the utility, they should have control over the demand at the consumer end. That is what is called the demand response, which will help in the energy efficiency. Okay. And anyway, these are the things actually I want to convey. And one more thing actually I will show you. Yeah. Okay. Demand side management. Demand side management is also there. That those are the demand side managements. What is the difference between demand side management, DR? Demand side management utilities are already, all the DISCOMs and the distribution utilities, they are already very much doing it. No problem. But I mean, they have a lot of experience also. But the demand side management is, it deals with those utility activities designed to influence customer use of electricity in ways that will produce desired changes in the utility's load shape, changes in the pattern and magnitude of the utility's load. That means the utility will change the loads and the peak load shavings. All those things will be done by the utility. There are six commonly referred to load shape changes. These are peak clipping, valley filling, load shifting, energy conservation, load growth from new efficient uses of electricity, and flexible load shifts. Of course, these are some of these, academic. But anyway, these are the things. What is then demand response? Those are demand side management. And now demand response. Demand response means individual consumer or individual customer activities designed to influence consumer demand in the short term, principally to reduce the peak demand. So this focus here is the peak demand. He has to control. If he controls the peak demand, it is demand during peak period, the peak hours, as the information provided by the utility through the smart grid signals arrangement. So that will help in the overall loss reduction and ultimately in the carbon footprint, reduction in the carbon emissions. And typically they includes load management, direct load control, time of use, real-time pricing, and critical peak pricing, etc. Dynamic energy management infrastructure applied to a generic billing. Of course, they have given also the billing is equipped with smart energy efficient end-use devices. With the end-use devices are equipped with smart components like energy management. These sensors are provided at the end-use equipment, end-use devices. Those sensors will pick up the signals and then they will control the systems, automated controls with data management capabilities, distributed energy resources, including storage systems. So like this, impact of the increased demand response, impact of the increased demand response by 2030. This is the report I picked up from the EPRA. This is the EPRA report. And you see, it says, I just show this. Energy savings estimation for a DR event, EPRA technical report. This is the technical report reference here. This is the report of EPRA. EPRA means Electric Power Research Institute, US, that is in Palo Alto in California. So that is the US based this thing. A lot of research, the studies they make for the country, and not only country, but throughout world. EPRA reports, EPRA, they are engaged. Okay. Here, This is the peak shaving. You see here. This is the load duration curve, energy saving potential, unconstrained peak loading. This peak load, if you control the peak, here I have given here just one example. If you control the peak in 1 kilowatt, that will be 1 kilowatt if you control in the peak, which may result into 65 kilowatt hours. Yeah, that means in the peak hour. Peak hour is different from your other non-peak hours. The management, the distribution will be different. If you control the peak hour, during peak hour, if you control the 1 kilowatt, which will be equivalent to 65 kilowatt hours. This is what.
Sir, one request, sir. Sir, please one request, sir. Please conclude. I request you to please conclude within 5 minutes, sir.
I'm going, sir. I'm going.
Thank you, sir. Thank you so much.
So that means the peak is the peak hour control. Here I have put here. Yeah, here I have put here. You see, the average ratio calculated for DR event was 65 kilowatt hours of energy saving for each kilowatt of peak demand reduction. See, losses during peak hours will be different from non-peak hours. That even any textbook equations are very much there. That any textbook will give you us. But that is what is required here. That is what is to be looked into. 1 kilowatt during a peak hour, if you control, that may result into this much energy. Impact of enhanced energy efficiency. See, anyway, summary of support of new utility business models, mechanisms for energy savings and carbon emission reductions, the accelerated deployment of energy efficiency and demand response through superior measurements and verification capabilities, innovation in devices through open standards, regulation. So some of them I have given here briefly. Yeah, I will come.
Sir, please conclude, sir. Please, sir. I am Honorary Secretary Ramesh.
Summary of smart grid benefits. I'm just closing, sir. Just 1 minute only. Smart grid has the potential to benefit the consumers, utilities, and environment, and the nation as a whole. Benefits include mechanisms for energy savings, GHG reductions, emissions. That GHG is a greenhouse gas emission. Greenhouse gas means basically carbon dioxide. Then briefly, the benefits are consumers. Better consumer service, improved communications, more service options and all that. That is utilities, improved communications, enhanced peak load management, relief during capacity constraints, reduced line losses and transmission congestion. This is dynamic pricing and auto distribution, auto DR, that is the demand response, like this. Environmental side, the benefits to the environment, grid interconnection of renewables, reduced resource depletions, mitigation climate change, improved air quality, waste minimization, and the country, what are the advantages to the country? Improved grid reliability, increased sustainability, economic development, ease of compliance with the national and international commitments. What are those commitments? Basically, the carbon commitments. India has committed to 500 gigawatt of renewables and net zero by 2070. All those commitments.
Gandhi sir, please conclude, sir, because all the seniors
are there. Sir. Conclude. Smart grid. So smart grid is the key enabler.
Completion was 6 o'clock, sir. It is already 10 minutes delay. Please, sir. Please.
Smart grid will enable tools for everyone, from consumers to energy service providers, regulators, help bring energy savings and your greenhouse gases reductions closer to the fruition to benefit the society. Thank you, sir. Thank you very much, sir, for giving the opportunity to just give my own thoughts, and probably it will have some impact on the definitely on the system.
Thank you, sir.
Loss reduction. Thank you, sir.
Thank you, sir. Gandhi garu chala baga chepparu. Highly appreciable presentation, and our in chat also so many people are highly appreciative. we are stressing about the main power grid and the loss of reduction is nothing but energy consumption, sir. Very happy, sir. Very happy,
Thank
sir.
you, sir.
Our eminent engineers, sir, Dr. Rameshwar Garu, Dr. S. Raj Garu, Brahmadi Garu, all are here. Dr. Jidhar Vimal also. So thanks once again.
Thank you, sir.
I think there is no question answer, but any important is there? Kindly ask Konarao Garu. Any important? Kindly.
చైర్మన్ గారు మీ వీడియో క్లోజ్ అయింది.
ఇది రావట్లేదు ఎందుకో వీడియో టచ్ కావట్లేదు.
Thank you for your wonderful presentation and insight, sir. Thank you very much, sir.
Can we leave, sir?
Sir,
I can leave, I can close it?
Chairman sir, shall I propose
What
vote of
of
thanks?
Yeah, what of thanks?
Shall I propose, sir, Chairman?
Yeah,
sir?
kindly go for what of thanks, sir. Honor Secretary Garu.
So it's pleasure to propose vote of thanks today. Today is the Energy Conversion Day, which is on 14th December 25. I extend my thanks on behalf of IEI to all the engineers, those who have joined this Zoom cloud meeting conducted for the technical talk. So I extend my thanks to today's speaker, Dr. K.S. Gandhi Garu, who is giving very good lecture on energy loss reduction techniques in power distribution network. So I extend my thanks to our chairman, Professor Dr. Ramana Banwathu, for conducting in a decent way, in an effective way, this cloud meeting. And I extend thanks to our committee member from electrical, Professor P. Satish Kumar Garu, FIE convener, for being convener to this program. And I extend thanks to Engineer D. Rama, Joint Honorary Secretary, Professor Dr. Muhammad Moinuddin, Joint Honorary Secretary, and Engineer Venkat Shivanarayana Garu, Engineer Konda Manasa, Challa Ramesh, Engineer Amit Deshpande, Engineer B. Ravinder, Engineer Dr. D. Chandrasekhar, and Dr. G. Rameshwara Garu, Director ISKI, Dr. N. Bhupesh Kumar Garu, Engineer B. Brahma Reddy Garu, our past chairman, and Madam Shirisha Waggu, and Dr. Jitendra Kumar, Dr. S. Venkatesh, Dr. P. Narayana Garu, Dr. G. Kondalra Garu, Dr. Jagadish Garu, Engineer Ramkishan Garu, Professor Ramanjanel Garu, G. Ronaki Gopalakrishna Garu, Madam Somishetty Usharani Garu, Engineer Anand, Engineer R. Raghav Garu, who participated from Varangal, and Engineer V. Balu, Engineer Dr. G. Venu, Engineer Muhammad Khan, Engineer N.S. Rao, Engineer P. Kondalra Garu, and Mandav Rajeshwara Garu, Engineer Sajjan, Engineer Shankar Jangama, Engineer Swaranana Saripalli, Engineer Siraj, Engineer V. Shailaja, Engineer Viru Nayak, Engineer P. Venugopal, and Madam Boda Anusha, and Engineer Jatoth. So I thank one and all for this. If I forgotten anything, I'm sorry. So with this, I conclude my vote of thanks.
Ratam Garu, Janamana Petty.
I request to raise all of you.
अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Jai Hind.
Jai.
Jai Energy Conversion. అందరికి సాయంకాలపు నమస్కారాలు. గుడ్ నైట్ ఆల్ ఆఫ్ యూ. రామేవాడ అందరికమ్మా.
Switch off.
కంగ్రాట్స్. గారు బాగా చేశారు. ఎన్ఎస్ రావు గారు బాగున్నారా? కొండలు సార్ నమస్కారం. బ్రహ్మణ్ సార్
నైస్ అండి, చాలా బాగా కండక్ట్ చేశారు. కంగ్రాచులేషన్స్.
సార్ థ్యాంక్ యూ సార్. 54 మెంబర్స్ చేయాలి సార్. కంగ్రాట్స్. థ్యాంక్స్ అందరికి.
మంచి రెస్పాన్స్ వచ్చింది.
నారాయణ సార్ ఉంటుంది కదా సార్. నారాయణ సార్ ఉన్నప్పుడు 54 మెంబర్స్ బాగా వచ్చారు సార్. థ్యాంక్ యూ.
ఓకే.
ఆమె ఇన్స్టిట్యూట్ సార్. నారాయణ సార్ మీకోసం కూర్చున్నా.
ఏయా ఏంటి? నేను ఇంటి దగ్గర ఉన్నాను.
ఓకే సార్.
నమస్కారం. ఇంటి దగ్గర ఉన్నాను.
నమస్తే సార్, అందరికీ నమస్తే అండి.
అందరికి నమస్తే సార్. రాఘవ్ సార్. రాఘవ్ సార్
నమస్తే నమస్తే సార్.
థ్యాంక్ యూ సార్. రాఘవ్ సార్ ఇచ్చారు బాగుంది.